All right, so just taking some time to go through and look at the questions that may come up on the exam. So what I want to do here, I want to show you, let's see here. There we go. I want to show you let me go over here. Okay. In positive physics under the assessment, I think this might be just questions about concept base or something to that effect. So they're going to ask some questions about the types of energy, but make sure you look carefully at what you see here where it says neglect loss. And as you have noticed, it's asking you to identify the energy types present at each time for the highlighted object or system relative to the reference level shown. Here's the reference level. So this is where height is 0. Notice here at B, this is not 0. So at A, when he's holding it, she is holding this. When they're holding it at A, that means there is gravitational potential energy, but it's not moving, so there's no kinetic energy. We could check that and make sure it's correct, and it is. And then at B, after it's allowed to swing, it's swinging at its maximum speed down here, but it's still not at 0. Reference level is 0. So this actually carries two kinds of energy, GPE and kinetic. Checking that, yep. And then when it goes back up to C, it stops. Right? You let go at A, it swings down through B, it comes up to C and stops. So that means no more kinetic energy, so it's all gravitational. Now, next question, similar. So this asks, an angry physics student releases the wrecking ball as shown. Are there other types of physics students? But just, yeah, I digress. The wrecking ball is just about to hit the building at the final time. Neglect loss. Again, this is the important part. Neglect loss. So identify the energy types present at each time for the highlighted object or system. So in the initial, it's gravitational potential being held. Then it's let go. Here's the reference level, and as it hits the building, it's kinetic, but it's also not 0. The reference level down here is 0, so it's kinetic plus gravitational potential. And we're checking that. Okay, so then on to the next one. So again, it says student releases a physics card on a track as shown. Apparently the physics student's not angry this time, but we are still going to neglect loss. So at A, at the reference level, being way down here, a student releases a physics cart on a track as shown. At A, if it's released, that means initially it's just gravitational potential. It's not moving. We'll double check that, and we are correct. Then at B is the middle section right here where it's moving and it's reducing its height, so it has both gravitational potential and kinetic. Very good. And then at C, it reaches the reference level, so it no longer has gravitational potential, but it only has kinetic. And we'll check that, double check. Very good. Now these spots are saying, what's happening here? And what's happening here? So this is saying work, loss, work and loss, or neither. So remember, work is a force applied through a parallel distance, and we don't have that. And loss, it says right here, neglect loss, so we're not going to count that. So it's neither. Double check. Perfect. And then again, same thing here. There's no applied force, so there's neither. Now, it's not to say there's not a force acting on this, because we know mg is pulling this way, and the normal force is pushing perpendicular, so the normal plus mg gives rise to the incline force, which is causing it to roll down the incline. So there's two forces, the normal and the weight. Normal plus mg gives rise to the incline, but there's no force times distance that's parallel to this thing acting on it, so that's why. Okay, next, that's a slingshot, same kind of thing. Now, this is another. Initially, a car is at rest at the initial time. A student pushes the car to the right, neglect loss. So we have two things. Car is at rest, that means it's not moving, and its reference level is 0, so the initial is none. There's no movement. There's no height. Checking the answer on that. None. And then as it's being pushed, also identify if loss occurs and or work is done by a non-conservative force between each time. So initially there's nothing, and then at the end there's no gravitational potential energy, but there is definitely kinetic energy. So how do we go from nothing to kinetic energy? Well, work is done. So work is added from nothing. We add work and we get a change in energy. So that's how you know what to do here. Okay, next. This is just straightforward. Mass is given 70 kilograms. These are really straightforward, so I'm not going to really spend a lot of time on those. Same kind of thing here. Force of work, force of loss, etc., etc. Force, remember force. Pedaling generates 60 newtons thrust. That's the force of work. She also experiences a 30 newton drag. That's the force loss. Okay? And then here we go. We're at a released at the top. Curved ramp or a roller coaster is shown, and assume the cart remains in contact with the track. Neglect loss, and this is to say there's no friction. Where does the cart have the greatest total mechanical energy? And it should say at the lowest point F, because at A it's released, so there's 0 of kinetic, but a fairly significant amount of potential. However, comma, the total mechanical energy is conserved if we're neglecting the loss. So that should read all equal. We'll check that answer real quick. Yes, indeed. Where does the cart have the greatest gravitational potential energy? Well, that's the highest point. So that's at A. Highest gravitational is there. Where does the cart have the greatest kinetic energy? That's at the lowest point because it's all transferred. So that would be at F. So it's moving the fastest at F. And where does the cart have the greatest speed? Also at F. And then where does the cart have the greatest tangential acceleration? Let me check those. All good. Tangential acceleration. So acceleration on probably the steepest curve, I would think, B and E. I don't know. Let's just see. Let's see what it says for us at B, because I think that might be the steepest curve. Check. Yeah, so steepest curve is the tangential acceleration. Okay, next. Those are just definitions. We're not going to go through those. Okay, so here, use conservation of energy to determine the unknown energies. So no initial, so this is 0 joules of work. Let me double check that. So the work done here, if the loss is 1,000, the work done here has to be equal to the change in energy at the end. So the total energy change is 6,000 joules of gravitational, 1,000 joules of kinetic, for a total of 7,000 joules. And then there was a loss of 1,000, so there should be 8,000 joules of work entered. So 8,000 joules of work with a minus 1,000 joules of loss should equal the total energy change, which would be 7,000 joules. So 7,000 joules. It's not letting me do that right now. I don't know why. I don't know what's the deal here, why we're 7,000 joules. So we have 6,000 joules of gravitational potential and 1,000 joules of kinetic because of the height and the speed. So there's 7,000 joules of total energy. 8,000 joules of work went in with 1,000 joules of loss, which would equal this 7,000 change. So checking that, yeah, that's what we're looking for. Okay, so the total energy at A, there's none. That's 0 joules. 57,000 joules of work is put in. So the total is 57,000. The initial height of the ball was neglected. To use the conservation of energy to determine the unknown energies. Total energy of the work is 57,000 joules. So the energy total would be 57,000 joules. We'll double check that real quick. Yeah. And that means there's 20,000 joules of kinetic and 37,000 joules of gravitational potential. Checking that, yes. So no work or loss. Total energy then would be 57,000 because that's consistent with the total here. It started with 0. We put 57,000 joules of work into it to get 57,000 joules of energy. That stays the same. Gravitational potential energy at C is where it stops, and that's going to be also 57,000 joules. Checking that real quick. There it is. Okay, so here we go. We're coasting here. So at A, the gravitational potential energy is 360 joules, so the total energy is 360 joules. We had a loss of 150 joules, so that means we had 210 joules of energy, 210, and it's all kinetic because it's at the reference level where height is 0, so that's all 210. All kinetic, double checking that, yeah. And then 30 joules of work was put in with 90 joules of loss. So 210 plus 30 is 240 minus 90, right? 240 minus 90 is 150 total energy, 150. And 100 joules is gravitational. That means there's 50 joules of kinetic. And we'll double check that. Boom, there you go. So you understand where there's 210 joules of kinetic energy or energy total, 30 joules of work was added, 210 plus 30 is 240, 90 joules of loss, 240 minus 90 is 150, and that's made up of 150 here. Okay, so you get the idea. Okay, so 2.6 kilogram cart released at the top of the ramp. That means the initial velocity is 0. The distance and the height of the ramp are shown. Neglect any friction and drag impeding the motion. That's huge. You guys understand that, right? So the initial at this height is all gravitational potential, and that's equal to mgh, and then we plug all that in and put it in there, and then it's going to say how much work was there. No work, because we're neglecting friction and drag, and work has to be a force directed in the same parallel direction as the movement or the acceleration. No loss, because we're neglecting friction and drag. And then the final energy is all kinetic energy because it's at the reference level, so there's nothing left. And then you can do your own math here. KE is 1/2 mv squared, GPE is mgh. Okay, same thing here, right? So same kind of deal. We're just looking for where's the work put in, where's the change. Oh, here we go. 600 watts of wind power for 17 hours. So a watt hour is 600 times 17. The kinetic energy is converted to electric energy and stored in a battery before used by a 40-watt light bulb. During the process, 79% of the energy is lost, which is pretty typical, by the way, for wind. So the wind energy captured is going to be 600 watts times 17 hours. So 600 times 17 is 10,200. 10,200 right here, 10,200 watt hours. And the loss is 79% of that, which is 0.79, which is 8058. 8, oh wait, not 6, 8058. And we'll double check those answers, make sure we're good. Yeah, that's 79% loss. And then the energy delivered to the light bulb is the difference. And then how long could the light bulb be used? So what you're going to get here is the difference between 10,200 minus 8058. I'm sorry, 8058. And that's 2142. 2142. And that's watt hours. So if we take that divided by 40 watts, so 2142 divided by 40 watts is 53.6. 53.6 hours. And we'll check that double. Yeah, 53.55 is what I got, but that's all right. And that's that. And then the same kind of thing here, remembering that the cart at the top, this is the one where the mg pulling down is the only force acting in the circle, so that's 1/2 mv squared is equal to mg. So the velocity here is square root of gr. And remember too that it's got kinetic and potential. Gravitational potential plus kinetic here is equal to the gravitational potential here. That's how you calculate h. H is going to be just a little bit bigger than 25, maybe 30-ish. Okay, now this is another one that's really kind of cool because the mass doesn't matter. The height is the only change. So the V final at the bottom is going to be equal to square root of 2gh. 2 times g is 19.62. 2g and times h, and then take the square root of that. So 19.62 times this height, take the square root of the whole thing, and that'll go here. Okay? Well, I hope that works out for you. I hope you guys do well with all those things, and I hope this video was helpful to get you through some of the potential rough spots. All right. See ya.